Hello there, Math 126 students. Somebody's asking me this question on the fall 2016 final. Just for that person, I'll talk about that question in just a second. For that person and for anyone else who finds this, keep asking me questions on the discussion board. I do want to note that if you go to my website, go to archive, there are some direct links. There's a playlist of bunches of stuff, but you're looking for the 126 exam prep. If you click on View Full Playlist, that's probably the best way to go because I have a lot of final exam review stuff here. So this is sort of, here's the strategy, here's what you should do. Here's a quick review of Chapter 12 and 13 skills, which we're about to do a problem like that, and I do several problems. And then I do a Chapter 14, Chapter 15 Taylor series. So that's kind of a quick series of if there's you want a quick recap. Okay, so let's look at this. The student is looking at this exam. They're given one of these Chapter 12 vector questions, I would call this, something about a parallelogram. And they give you some points. So let's note a few things. A is 1, let me use a different color. 1, 2, 4. B is 2, 0, 5. C is 4, 6, 0. And I think that's it. And it says, find the coordinates of D. That's not so bad. So the big idea, if you're asked for a coordinate, is to turn things into vectors. For example, let's just pick one. If you did BA, so remember you do your subtraction. Think of B as the tail. That's the thing that you're gonna subtract. And you're subtracting that from A, so it's 1, 2, 4. So I'm getting -1, 2, -1. And that represents the changes. So if you're doing a double check, you would say, did I go down 1? Yes. Did I go up 2? Yes. Did I go down 1? Yes. So as long as I copied down those numbers correctly, then I did this subtraction correctly. And that's a nice little check to build into your routine. Now this vector should be the same if it's a parallelogram. So this is also the same as CD. And that means it's the same changes. So to go from here to here, it should be down 1. And this was not what the person was asking about, but this is actually the same principle. Then up 2, then down 1. Okay. So the question the student was asking was the question on the next page, which had to do with finding that point E. So let's go back up and look at it. And they give you the two pictures because they're trying to say we don't know which picture it is. The point E, though, is a point you get from a projection. So let's sort of recap a few things. So strategically here, I don't know why I just erased that because I need a piece of it. So we're going to make a note that I have this is BA. And I'm going to erase this other stuff. So my first observation or my plan is to figure out the vector BE. If I could figure out the vector BE or some other vector there, but let's say BE. Hey, I'm not answering this question now. I'm looking at the other one. I already know B, so then I can use the same trick. So if I could figure out what this was, let's call it change in X, change in Y, change in Z, then I could figure out what the point E is by just adding those changes like we just did. So what's hard about this problem is you have to have this plan that if I can figure this vector, then I am done. This vector BE. Because then I can add in the same way we just did. All right, so you have to have that forethought in doing this problem. The way I do this is I just go, I'm going to do a projection. It turns out it doesn't matter what the picture is, whether it's this one or this one. The way you do this length is the same. And that's that projection length. So I always remember it's whatever your project. So the ground in this case, I need some vector that points on the ground. So how about I use CB for the ground? So you could also use BC. And you'd have to interpret. But I'm going to use CB. So let's compute that vector. So 2 minus 4 is negative 2. 0 minus 6 is negative 6. 5 minus 0 is 5. We can do a double check. Down 2, down 6, up 5. Okay. So I would like to project AB onto the ground. And it's fairly easy to remember this formula. It's the dot product divided by the thing you're projecting onto. So this would be the ground. So in this case, I would do, let's see, I want to project ABA onto CB, and the ground, the thing I'm projecting onto, is CB. This is how I do it. I don't even think about formulas anymore because I find that the formula, like just writing it, tends to confuse students. So I just compute this number and then I'll figure everything out from there. So I'm going to do the dot product of these two things. So that's going to be a 2 minus 12 minus 5. That times that, that times that. Divided by the length of CB. So it's the square root of 4 plus 36 plus 25. So I'm getting that this is, let's see what that is. And person who asked this question, check my arithmetic. Give me a follow-up if you got this. So that's what I get. I'm really tempted to simplify it, so let's do it. Square root of 9 times the square root of 5. So it's 15 over 3, so it's negative 5 over square root of 5. Oh, it simplifies even more. Because you can multiply top and bottom by square root of 5, and so it's negative square root of 5. Oh man, that always confuses people. Sorry if it did. I have this length now. At this moment, I have enough to finish the problem. What do I mean by that? So now I can find the vector BE. The fact that it's negative actually tells me something. It actually tells me it's this picture. Because when I did that projection, it was this negative. So anyways, negative root 5. But that's beside the point. I want to find the vector. I guess the other comment to make is when I'm doing, if I'm thinking about the angle between them, I should draw them tail to tail. Now they aren't drawn tail to tail. So if I had drawn BA, and CB, just to give another reason I know which picture it is, and I want to know the angle between them. If the dot product is 0, they're perpendicular. If the dot product is positive, it's an acute angle. And if the dot product is negative, it's an obtuse angle. So the fact that the dot product was negative tells me this is not the right picture. It should be more than 90 degrees. So that's the other reason I know it's that picture. All right. We then rescale. We're going to rescale this vector. You don't even have to think about what I just said to do that part. And we want it to be this length. So I'm going to take the vector CB. I'm going to make it a unit vector. And this is what you get from the projection formula. And then I'm going to multiply by this desired length. And we could have done all of this automatically. Anyways, negative square root of 5. The length is this 3 root 5. 3 root 5 we already found. And then I'm going to multiply it times CB. CB is negative 2, negative 6, 5. This is also what you would get if you had used the vector projection formula of BA onto CB. So anyways, what I get is, when all of this is said and done, I get that BE, which is this vector I'm trying to find, is this thing. So negative 1/3 times negative 2, negative 6, 5. And so you get 2/3, 2, negative 5/3. And again, a formula would be fine. This is the component projection and this is the vector projection, but I really just think of it as a rescaling of that vector. The fact that there was this negative here is why, another reason that I know it's pointing the other way. Now that I have that, I know how to get from B to E. So that's usually the confusing part because we've already done so much work. But since I know that B is 2, 0, 5, and this is how you get from B to E, that means E is going to be 2 plus 2/3, 0 plus 2, and 5 minus 5/3. Okay, let me know if that's not matching the solution, but I hope that gives some background. And thank you for being one of the first to ask an old exam question.